In this session, we look at joint distributions of functions of random variables. So recall that when we were talking about if x was a discrete random variable with a PMF f sub x, and y was a discrete random variable which was a function of x, y equals u of x. And if this was given by a one-to-one transformation, then we ask what is f sub y, right? So supposing we have a joint distribution, then what happens to if we have a joint distribution for x1 and x2, and y1 and y2 are functions of x1 and x2, then can we work out what the joint distribution of what for y1 and y2 is? Well, in the case of a one-to-one transformation, yes, we can. So supposing that x1 and x2 are discrete random variables, and they have a joint PDF f sub x1, x2, and y1 is a one-to-one, y1 and y2 are given by a one-to-one transformation. Y1 is equal to u1 of x1, x2, and y2 equals u2 of x1, x2. And the inverse, and you can find an inverse transformation. X1 is equal to w1, y1, y2, and x2 equals w2, y1, y2. Then the PDF f sub y1, y2 is given by f sub y1, y2 of y1, y2 equals f sub x1, x2 of w1, y1, y2, w2, y1, y2. Okay, here's an example. So let's say there are two independent Poisson random variables, x1, x2, and they have rates lambda 1 and lambda 2. Let's define two new random variables by y1 equals x1 plus x2 and y2 equals x2. Let's find the joint distribution for x1 and x2 first before we find the joint distribution for y1 and y2. So we were told that the x1 and let's say we're given that x1 and x2 were independent of each other, two independent random variables. Then their joint PMF, their joint PMF will be the product of the individual PMF. So the joint PMF f sub x1, x2 is the product of f sub x1 times f sub x2. Now, what's a PMF for a Poisson random variable with rate lambda 1? Well, it's e to the negative lambda 1 to the x1 over x1 factorial. And for another Poisson random variable with rate lambda 2, its PMF is e to the negative lambda 2 to the x2 divided by x2 factorial. And if we multiply the two of these together, that will give us the joint PMF, since we were told that x1 and x2 are independent random variables. Then this will give us e to the negative to the power lambda 1 plus lambda 2, lambda 1 to the x1, lambda 2 to the x2 over x1 factorial, x2 factorial. Now, so we found this is how we would find the joint PMF in this case for x1, x2. In the continuous case, with a joint distribution, if you have x1 and x2, they're continuous random variables, and they have a joint PDF f sub x1, x2, and the new random variables are given by y1 is equal to u1 of x1, x2, and y2 equals u2 of x1, x2. And U1 and U2 are one-to-one functions, so we can find inverses. X1 equals W1 of Y1, Y2, and X2 equals W2 of Y1, Y2. And then the joint PDF for Y1 and Y2 is given by F sub Y1, Y2, evaluated Y1, Y2, is F sub X1, X2, evaluated at W1 of Y1, Y2, W2 of Y2, Y2, right? Multiplied by the absolute value of the Jacobian determinant, and the Jacobian is this one of this matrix, partial of x1 with respect to y1, partial of x1 with respect to y2, partial of x2 with respect to y1, and partial of x2 with respect to y2. So you find that determinant, if it's negative, well, you just take the absolute value of it, and then you multiply. Okay. So suppose that f sub x1, x2 of x1, x2 equals 4x1, x2. X1 goes between 0 and 1, x2 goes between 0 and 1, and you get 0 for the joint PDF otherwise. And let's say you make this transformation, y1 equals x1 squared, y2 equals x1, x2. Then how do you find the joint PDF for y1 and y2? Well, you do it this way. You find these inverses, right? And then you find the Jacobian for these using these inverses. Okay. And then you put it into this formulation. That will give you the result. And you should do this exercise to make sure that you understand that. Okay, so now that we have the basic definitions down, where do we use these a lot? These would be in things like expectations, variances, covariances, and correlations, right? So supposing that x and y are random variables, they have a joint PMF f sub xy, and g of xy is some real value function of x and y. Then for discrete random variables, the expectation of g, which is a function of x and y, we also write it as e of gy. We sum over the allowed values of x and the allowed values of y, g of xy times the PMF. And that's analogous to the case where there's just a function of a single random variable. It looks a lot like this, except you have to do a double sum over x and y instead of just a sum over x. And in the case of continuous random variables, if you have mu sub g of xy, the expectation of g of xy, well, you integrate g of xy times the joint PDF f sub xy over all values of x and y. Okay, so once again, this is analogous to the single variable case. But in the single variable case, you would just integrate over all x. And here, you integrate over all x and y for a function of two random variables. Okay, so suppose x and y are uniformly distributed on the unit disk. What's f sub xy? Okay, well, f sub xy is equal to 1 over pi for xy on the disk, 0 otherwise. Why? Because the area is pi. So if you integrate over that area, you're supposed to get 1. Right? So f sub xy equals 1 over pi. It's a constant. It's uniform. Right? So now, if I had this g of xy equals root of x squared plus y squared, then what's the expectation of g of xy? Well, you have to integrate over all x and y, g of xy, f sub xy, over the area well, over all the plane, except most of that is zero, right? The only non-zero part is the part on the unit disk. So you have to do the double integral over the unit disk, and then g of x, y, f sub x, y, sorry, has the form 1 over pi, and g of x, y has the form root of x squared plus y squared. Now, if I convert to polar coordinates, root of x squared plus y squared is r. So that's the integral over the disk of r. And what's dA? The area element in polar coordinates is r dr d theta. So that's 1 over pi. Now you're using polar coordinates, so theta equals 0 to 2 pi, r equals 0 to 1, that covers the disk, r dr d theta. But then, so combine the r's, you get r squared. So now if you do that integral, it works out to 2/3. Okay, so that's the expectation of that function g. Okay, supposing I've given a function f sub x, y, z of x, y, z, that's a joint distribution in 3 dimensions, and that's equal to 4 times x, y, z squared over 9 for x going between 0 and 1, y between 0 and 1, z between 0 and 3. So that's a solid cube in 3 space, and it's 0 elsewhere. We want to find the function, the expectation of x plus y plus z over 3 space. Okay. What's the sum of an expectation? What's the expectation of a sum of random variables? Well, okay. So that's one thing that you could use before doing this, maybe. You can see that the expectation of x plus y plus z is the expectation of x plus the expectation of y plus the expectation of z. This will require a triple integral for you to do, or maybe 3 triple integrals. Okay. What's the expectation of a sum of random variables? So x and y are random variables. They have a joint PMF f sub x, y. They have individual PMFs f sub x, x, and y. Then expectation of x, y, of x plus y. Well, we just start with the definition, sum over all the allowed. Do a double sum over x's and y's that are allowed. And then we grind through the algebra. And what do we get? We get the expectation of x plus y is the expectation of x plus the expectation of y. And it reminds us of the single random variable case. Okay, the sum of finitely many ones, expectation of x1 plus x2 up to xn. Well, it's the expectation of x1 plus the expectation of x2 plus, and so on up to the expectation of xn. Okay. For 2 continuous random variables, well, let's just do it again. You just use the definition of expectation in the continuous case, and you'll get that the expectation of x plus y is the expectation of x plus the expectation of y. And that generalizes to n random variables. Okay. What about functions of random variables? Expectation of g of xy plus or minus h of xy is the expectation of g of xy plus the expectation of h of xy. Okay. Now we come to the covariance. So an example of a covariance. It says, supposing x is the number of students that are given to LUMS, they're going to come to LUMS for a given academic year. Y is the number of TAs hired for the first semester courses. Now these things should be should be linked in some way. If we admit more students, then we should hire more TAs. If we admit fewer students, we would admit fewer TAs. Okay. So we want to know how we might want to know how these go together. So this is how we look at the relationship between two different random variables. We see how connected they are. Supposing that x and y are random variables with a joint distribution f sub xy, the covariance of x and y is defined to be sigma of xy. Some people write COV of xy. That's equal to the expectation of the difference between x and its expectation times the difference between y and its expectation. That's the definition of the covariance. So it's a measure of the linear association between x and y and leads us to the discussion of correlation. Right now we're working on covariance. Okay. So it turns out that if we play around with it a bit, this is the same as the covariance of x and y is equal to the expectation of x and y minus the product of the expectation of x times the expectation of y. Okay, so that's another way of calculating it. Okay, so here's an example. X and y are discrete random variables. Sorry, they're continuous random variables. They have a joint distribution. Oh, sorry, getting confused here. These are discrete random variables. They have a joint PMF defined by f sub xy equals 1/3 if the ordered pair xy is equal to 1, 1. 1/3 if xy equals 0, 0. 1/3 if xy equals minus 1 and 1. And it's 0 otherwise. What's the covariance? Well, the covariance is the expectation of xy minus the expectation of x times the expectation of xy. So to find the expectation of x, right, you take you take x times the various probabilities. So this would be 1 times the probability of this ordered pair is 1/3 plus x is 0 times the probability of this ordered pair 1/3 and x is minus 1 times the probability of this ordered pair, which is 1/3. So 1 times 1/3 plus 0 times 1/3 plus minus 1 times 1/3 is equal to 0. That's the expectation of x. What's the expectation of y? Well, it would be this y value is 1 times its probability is 1/3. This y value is 0 times its probability is 1/3. And this y value is 1 times its probability, which is 1/3. So 1 times 1/3 plus 0 times 1/3 plus 1 times 1/3 is equal to 2/3. That's the expectation of y. What's the expectation of xy? The expectation of xy is 1 times 1 times its probability, 1/3, plus 0 times 0 times its probability, 1/3, plus the minus 1 times its probability, 1/3. That's the expectation of xy, and that's equal to 0. So now the covariance of x and y is equal to the expectation of xy minus expectation of x times the expectation of y. That's 0 minus 0 times 2/3, which is 0. So the covariance is 0. When the covariance between two random variables is found to be 0, then we say that the variables are uncorrelated. Okay, suppose that we have two random variables x and y, and their PDF is f sub xy on xy is equal to x plus y. It's on the unit square and 0 otherwise. So as an exercise, find the covariance x times y. Okay, some properties of the covariance. Covariance of x and y is the covariance of y and x. The covariance of x and x is the variance of x. The covariance of ax y equals a covariance xy. And the covariance of the sum of a bunch of random variables with the sum of a bunch of random variables is the double sum covariant of the individual covariances. Once again, two random variables are uncorrelated if their covariance is 0, otherwise they're said to be correlated. And if you have a whole bunch of random variables x1, x2 up to xn, they are said to be uncorrelated if all the pairwise variances are 0. Okay. So here's a problem. If x1, x2, x3, and x4 are pairwise uncorrelated random variables having a mean, having an expectation of 0 and a variance of 1, compute the correlation of x1 plus x2 of the new random variable x1 plus x2 and the new random variable x2 plus x3, and compute the correlation of, compute the covariance, not the correlation, compute the covariance of the new random variable x1 plus x2 and the new random variable x2 plus x3, and the covariance of the new random variable x1 plus x2 with the new random variable x3 plus x4. Okay. Covariance then brings us to correlation. So the idea of covariance is to see if two random variables vary with each other, opposite to each other, or independently of each other. But we could get all sorts of numbers for the covariance. And then it's hard to compare covariances one with the other. So if we normalize this, we can get a bit more out of it. So we come up with a new measure, which is called correlation. The correlation is equal to the covariance, the correlation of x and y is equal to the covariance of x and y divided by the standard deviation sigma x, sigma y. Okay, so the correlation rho xy is equal to sigma xy divided by sigma x divided by sigma y. That's a measure of a covariance, but it's normalized such that it lies between -1 and 0. Okay. Supposing that I've got this, I've got x is a random variable and y is equal to ax plus b. You should be able to show from this definition that rho xy is going to be -1 if a is negative, and it's going to be +1 if a is positive. Okay. Here's a problem. Supposing that I have discrete random variables x and y, they have a joint PMF f sub xy, and it's given by the PMF for 4, 1 is 0.15, for 4, 2 is 0.15, for 8, 1 is 0.15, for 8, 2 is 0.45, and for 12, 1 is 0.01, and for 12, 2 is 0.09, and we ask what is the correlation rho sub xy. Okay, so let's do the calculations that we need. We want the expectation of x, so we sum over x and y, x times the PMF for xy. If we do that, we get 7.12. Now we also need the expectation of y. So the expectation y, we sum over all xy of y times the PMF f sub xy. And if we do all of those, we get 1.69. Now we need the expectation of x times y. So what do? You do the double sum over the allowed values of x and y of x times y times the PMF f sub xy. And if you do that, you get 12.48. Then the covariance is given by expectation of xy minus the expectation of x times the expectation of y, and you get 0.312. Now, the expectation of x squared, we want, right? That's the summation over x and y of x squared times the PMF, and that gives you 68.4. The variance of x is sigma squared of x. That's the expectation of x squared minus the square of the expectation of x. We've calculated these before, and we get 16.56. The expectation of y squared is the sum over the allowed values of x and y of y squared times the PMF, and that gives you 3.07. And now we can find the variance of y. That's the expectation of y squared minus the square of the expectation of y, and we get 2.139. And finally, what's the correlation? Well, the correlation is rho sub xy equals sigma of xy divided by sigma x divided by sigma y. That's equal to 0.312. We found was the covariance divided by, well, we found that the variance was 16.56 for x, so we take the square root of that for the standard deviation, and we found that the variance of y was 2.139, so we take the square root of that to find the standard deviation of y, and we get 0.0524. Okay, need to be a little bit careful. Correlation is not causation. Okay. Right, so babies that are held more tend to cry less. One might reasonably suppose that there is causation here, and holding babies makes them less anxious. On the other hand, correlation between GRE test scores and graduate school correlation rates at 0.39. Consider that a strong correlation, but doing well on the GRE is not the cause of, it's not causation of completing graduate school completion. Okay? So there's no causal link between the two of them. Okay. Now, you get some simplifications when you have independent random variables. Okay, so we go through a few of those. Expectation of a product of independent random variables. Okay, if x and y are independent random variables, then the expectation of xy equals the expectation of x times the expectation of y. That is not true in general, right? We're relying on the fact that x and y are statistically independent random variables. Okay, if two random variables are independent, then their covariance is going to be 0. But they are uncorrelated. So the correlation of independent, statistically independent random variables is 0. Okay, if I have a sum of independent random variables, x1, x2, x2, xn, then the the variance of this new random variable a1 x1 plus a2 x2 plus and so on up to xn. That's equal to a1 squared variance of x1 plus a2 squared variance of x2 plus an squared variance of xn squared. That's not true in general. We're relying on the fact that these are independent. If they weren't independent, you'd have a whole bunch more terms. Okay. All right. One thing to note, a covariance of 0 does not mean that x and y are statistically independent. Doesn't always happen. And here's an example. If I had x uniform on -10 to 10 and y equals x squared, you can do the exercise and you can see that the covariance is 0, but x and y are not statistically independent. So you can have covariance of 0 without x and y being statistically independent. Okay. Okay, supposing that you have random variables x1, x2, and so on, and they have a common expectation mu, and they have a common variance sigma squared, and y1 equals x1 plus xn plus 1 plus xn plus 2. So it's the sum of 3 of those. Find the covariance of y sub n and y sub n plus j for j greater than or equal to 0. Okay, so that would be an exercise for you to try. Okay, variance. Recall that if x1, x2, and xn are random variables, then the expectation of their sum is the sum of their expectations. Okay, so that's a nice property of the expectation. What about their variance? The variance of a sum of random variables is the sum of the individual variances plus these extra terms, summation I to n, summation j to n, variance of xi, xj. Okay, so if you have the variance of a sum of independent random variables, then this term over here with the extra term, well, not really extra terms, these terms are required when they're not necessarily independent, but if they are in fact independent, then the variance of a sum of random variables which are independent is just the sum of the individual variances. And if you have the variance of a linear combination of two random variables, say the variance of ax plus by, that's a squared times the variance of x plus b squared times the variance of y, plus this extra term 2ab variance, covariance of x and y. Now, if those two were independent, then what would happen? Okay. So that's the end of the session.